So hello, everyone. I'm Simon Marshall, and as was laid out, I shall be talking about improved separations. This is a work I did during my PhD when I was at LIDA under Vedran Dunjko. My apologies. I'm going to move this a little. Okay, hopefully no feedback. Okay, yeah, so this is a work I did while I was in my PhD under Vedran Dunjko at LIDA, and in collaboration with Scott Aaronson at UT Austin. I'm now at the AI Safety Institute, which is a part of the British government. Whoop, didn't mean to click so far, where I now work on complexity for AI alignment kind of stuff. Yeah, so what is this word salad of a title, and what does it mean? For me, this paper is about kind of one of the core questions in quantum computing, which is quantum computing fundamentally more powerful than classical computing? Can I actually do more with my quantum computers than I can do with my classical computers? Most people in quantum computing don't work on this question directly. They work on this question by attempting to come up with algorithms for a quantum computer that are better than the best known classical algorithm. But for almost all of these instances, if you told me that problem X actually has an efficient classical algorithm, my belief in everything doesn't fall apart. I still believe what I believe. So what I would really like is I would like to prove that these two are not equal, that fundamentally quantum computing is better than classical computing. And as is the standard in complexity theory, the default for this ends up being the decision theory problem of is BQP equal to BPP? Now, for that particular problem, for the decision theory problem, there basically hasn't been enough space to grab onto this problem and to try and show these two are separate. There's not, from my perspective, this isn't the strongest separation we have, the strongest proof. Before our work, the strongest proof to me was about sampling. So we have a proof from 2011 from Aaronson and Arkhipov that if samp BQP, if you can use your quantum computer to get samples, we'll talk what that means in a second, to get samples out that you couldn't sample from a classical probabilistic machine. So if you can't sample things if you can't sample from distributions on your quantum machine that you can find on your classical machine, i.e. if samp BQP equals samp P, then the polynomial hierarchy would collapse to the third level, or two conjectures about the permanence of Gaussians would fail. So I was looking at this paper at some point, and I was reading another paper by Fortnow and Feigenbaum from the 90s, and I realized that actually these two papers were basically connectable. And via a little bit of wiggling, you could bring the result down. So you could bring the result from if samp BQP equals samp P, then the polynomial hierarchy would have to collapse to the second level, i.e. one level lower. Now, I've talked to a lot of people at this conference who have told me in no uncertain terms that they hate quantum computing and they don't get it and they're not enjoying it. So I've got a gift for all of you, which is that this isn't a talk about quantum computing. This is a talk about exact counting versus approximate counting. So I will have to talk about a small amount of quantum computing, but I'll keep it very light. To show that the Aaronson-Arkhipov result is actually saying that if samp BQP equals samp P, then approximate counting is equal to exact counting. So, and then what we're going to do is we're just going to have this extra little add-on. You can forget all about quantum that says if approximate counting is equal to exact counting, then the polynomial hierarchy collapses to the second level. The way I'm going to go through this talk is just quickly give a definition of what I mean by approximate and exact counting. Then I'll outline the Aaronson-Arkhipov result, and I'll sort of justify to you why it's actually about counting. And then I'm going to go over the key steps of our proof. As I said, I'm now in AI, and this means that I need frequent and constant rewards in order to perform well. So if people can put on sad faces when they don't understand, that will lead to better performance. Yeah, so what do I mean when I say counting? Exact counting is, everyone's familiar with it, it's sharp P. So the classic problem here is counting sat of how many satisfying assignments do I find to some Turing machine. You give me a Turing machine and ask me how many inputs could I give such that it's happy with. And I just exactly count the number. Approximate counting is the same problem, but you're just looking for multiplicative error. So up to 1 + 1 over poly n, you're looking to get close to knowing the number in the sharp P case. And for these two classes, this little multiplicative approximation really reduces the size of the complexity class needed to calculate it. So to do exact counting, we need sharp p. To do approximate counting, we just need BPP to the NP in parallel. So BPP to the NP, probabilistic time machine with an NP oracle, and the parallel just means that it makes one set of oracle calls all in one round. We really need that parallelization. Any questions at this point? Great. Cool. Yeah, so two problems in this, we'll come to this in a second, is counting the 0-1 matrix. So exactly counting a 0-1 matrix is in sharp p. Approximately counting this is in BPP to the NP, but approximately counting a real valued matrix, doing this for all real value matrices, is actually again in sharp p. So you can, by approximately counting, approximating the permanent of a, I've written counting, my apologies, approximating the permanent of a real matrix is in sharp p. And this just comes down to the fact that if you allow me negative terms in my permanent, I can essentially use it to interfere different parts of the permanent and make it smaller, and thereby make my multiplicative approximation much closer to the actual answer. Cool. Now this is the quantum part. Go to sleep if you want. This is called this is an optical bench. And I'm going to be talking about a problem called boson sampling. So the most frequent boson you're all familiar with is light. You're using it right now. And boson sampling is the task of, if I give you a load of optical elements provided on a bench and I input a load of photons, can you then sample the output I would expect to see from this? So where would I measure my photons? And the big breakthrough, one of the big breakthroughs that Aaronson and Narkopov made is they realized that actually this optical bench was all noise. It was all just a mathematical problem, which is that if you give me any column orthonormal matrix, I can arrange my bench, I can arrange my experiment such that it's all about sampling submatrices of that larger orthonormal matrix. And of course, sorry, one thing I should add here is that you don't have to run this experiment on an actual bench, you can do it on your quantum computer. So of course, this is a problem that's going to be in SAMP BQP. This is what I mean by these submatrices, as that if you give me this column orthonormal matrix over here, and then you say, what's the probability of measuring the state 0, 1, 1, 0, 1? Well, there's a 0 in the first place, so I'm not going to take the first row. In the second row, there's a 1, so I'll take DEF, and in the third, I'll take another 1, and 4 I won't. So yeah, I build up the submatrix. And then the key insight here is if the problem in SAMP BQP, if SAMP BQP is equal to SAMP P, if my quantum experiment could be done on a classical computer, what I can do is I can then therefore sample from this distribution on my classical computer. If I can sample from this distribution on my classical computer, I could run my approximate counting algorithm on that sampling machine, and I could actually calculate the size of these permanents up to multiplicative error. But of course, the big insight is that I don't have to input a 0-1 matrix. I can put in not quite any matrix in the reals, but I can put in a matrix with negative components. And if I put in a matrix with negative components, as we saw a couple of slides ago, and if I can multiplicatively approximate that, that is a sharp P complete problem. So this is the breakthrough. Have I got a slide? Yeah. Where Aaronson and Narkopov take SAMP P equals SAMP PQP. They specify a quantum experiment. They say, okay, if this is equal to classical, then we can do approximate, then we can go through these steps and we can show that approximate counting is equal to exact counting. Any questions at this point? Awesome. So yeah, now we're going to move on to the more novel side of this. And this, now everyone who was asleep, wake back up. We can now talk about approximate counting and exact counting. So what we're going to say is, if approximate counting is equal to exact counting, then sharp P equals ZPP to the NP. So what we're going to, so exact counting, sharp P, approximate counting, BPP, parallel NP. There are like ways to make this more general, but this is slightly, this is the nice form of the argument. All the others can be derived from it. Yeah, so how am I going to get through these steps? What I'm going to do is I'm going to use the fact that I start from sharp P, and I'm going to use certain properties of this class that simply shouldn't be kind of allowed for BPP to the NP. I'm not actually going to use the super OP-ness of sharp P in the sense that any counting problem. I'm going to use like relatively trivial properties, like sharp P has random self-reducibility in it. And because it's randomly self-reducible, this is my next slide actually, is that sharp P, because sharp P can be randomly self-reducible, we're going to be able to make BPP to the NP randomly reduced to NP. We're going to get in a situation where we can answer sharp P queries by just asking random questions about NP or random questions in NP. And for those of you who really like the classic great papers, there's a really killer paper, which I really recommend reading, for this Feigenbaum and Fortnow in the 1990s, where they show that NP cannot be random self-reducible unless the polynomial hierarchy collapses to the third level. That's not the title, but that's the paper they put out in 1990. I checked the year. So if we're in the situation where sharp P is randomly reducible to NP, you can, I will explain, and you can see how tweaking this style of argument allows you to get another collapse, allows you to go slightly lower. And indeed, we're going to go down and we're going to say, hey, if you start from this approximate equals exact counting, we're going to get to the point where we can say sharp P is equal to NP slash poly intersection co-NP slash poly. Those of you who, this is super close to the Karp-Lipton result, which is that you get a polynomial hierarchy collapse if you get PH equals NP intersection co-NP slash poly. And when I was writing this result, I thought I just made the mistake of thinking that was equivalent to what was up there. I just ran an error. And for 2 weeks of my life, I was depressed when I realized they weren't the same, until my supervisor, I don't know if he intentionally waited just to play with my sense of mortality. He then showed me that there's this great paper by Arvind and Kobler, again, I think from the early 2000s, where they basically show exactly that collapse. So the collapse works out from them. But of course, I'll give a small intuition as to why that's true as well. Any questions? Cool. Yeah, so here's my nice graph so you can track it on the side. So for those of you who aren't aware what random self-reducibility is, so random reducibility is if you give me two problem classes, A, randomly reduces to B. Now, if I want to answer, is a certain number in A, or is a certain number in the problem A, I can answer this by just asking queries about B that are random and are drawn from distribution independent of the original input I was given. So, drawn this here. There are nice colors, but you can't see them so clearly. But this sigma is going to be a random query generator. It's going to generate queries to MP, and it's not going to depend. It's going to sample from distribution which is independent from X. G should be B. My apologies. And then there's going to be this bounded probabilistic time, bounded error probabilistic time, BPP phi, that is going to put them all together. And by querying NP, it's just going to run a probabilistic calculation and spit out the correct answer with high probability. Just the definition of random self-reducibility, but I didn't want to assume it. So the first result we need is this on the right, sharp P random reduces to NP. So we're going to assume the problem is calculating the permanent, and we're going to start by randomly self-reducing sharp P. So we're going to take an instance of, we're going to take the permanent, we're going to take a load, we're going to reduce it to a load of other random instances of sharp P. But of course, since sharp P is equal to BPP NP in parallel, I can just put these into my BPP NP machine. I can just plug in the random inputs I got. And of course, the oracle calls the BPP NP machine is going to make are going to be random as well. So I'm now in the situation where I have a randomized point. I give a load of randomized points. I make NP oracle calls, which are independent from the input. And then I run a BPP machine. I run a BPP calculation, and I get out the other side. And so, of course, this is also the definition of random reducibility. And I've got the situation now where I've got sharp P random reduced down to NP. At this point, you almost feel like this should be the OP result because NP seems really, really low. And in the future work, maybe this is something you can do. I believe that a more skilled complexity theorist than me should be able to. But I could not, and thus I have to now go back up the polynomial hierarchy. So the way we're going to go up the polynomial hierarchy is we're going to start, let's look at the direction of proving this class. If it randomly reduces to NP, then it's in the class NP slash poly. And in fact, let's go even easier than that. Let's show that it's in the class AM with polynomial advice. And the way we're going to show this is if you give me an input, let's say, and then me as Arthur, I'm gonna calculate the instances that I want random answers to, and I'm gonna give them to Merlin. And Merlin will return proofs to the instances that he thinks are solvable. So suppose I have 10, I'm gonna ask 10 random queries, and then I ask Merlin for proofs, he sends me back 4 random queries. Well, I know that the 4 he sent me proofs for are yes instances for NP. But there may be more instances for NP. It could be that 5 or 6 of the queries I asked were also yes. And this presents a problem because I have no way of telling that Merlin isn't just refusing to provide me a proof. And this is where the polynomial advice is going to be coming in, is that what I can do is, yeah, I don't know what the particular thing is, but because I asked random queries, I know that the average of the, queries, the average number of yes instances I should see should be some number, let's say 1/2. I should expect to see half my instances being yes. Now, if I ask one query and not all the instances are yes, that's not surprising. But I could just do this again and again and again. I could ask I could run my random reduction and then ask another random reduction and ask polynomially many random reductions. And in order for Merlin to lie on every single one of them, he would have to be noticeably far away from the average that he should be hitting. So he won't be getting close to the average number of yes instances you would expect to see. I apologize, I'm kind of like condensing the core argument to this paper down into like a sub-argument, but I really think this is one of my favorite papers to read. And there's like a whole series of them getting more insane. So it's a good paper if you haven't understood this. Yeah, so now we're in the situation where we've gotten down to it's inside AM/poly. And of course we can just de-randomize because we've got polynomial advice. So we can just ask for a good random string for all points as part of our advice string. If we get that, now you can just repeat this argument for co-NP, or you can come up with an argument about complements, doesn't matter too much. And you get down to in both NP and in both co-NP/poly. Now at this point, we're in this almost Karp-Liptonable result, where my supervisor, like a little wonderful person, comes and gives me a paper where they just politely, even in brackets, have put i.e. checkable sets in NP/co-NP/poly. The sentence before this even says that sharp P is a checkable thing. It required no mental activity from me at all, which is very nice. I'll give you some sense of why this result is true. That sharp P, so what a checkable set is a set where if you give me an algorithm that claims to solve this problem, I can, with high probability, tell whether your algorithm is correct. It works via the same mechanism that random self-reducibility works for in sharp P. But I'm basically going to take random points, I'm going to express them as other random points, I'm going to express those other points as random points. I'm just going to keep moving around and decreasing the size of the space, the same argument that works for IP. So the main reason that sharp P is in IP. And I'm just going to get down to a point where I can be sure that either your algorithm is wrong or your algorithm is right with high probability. And because I can do this, I can then use a ZPP NP algorithm to basically search for a polynomial string where I can where my checkability argument holds. So that concludes the proof. We went through, we said, hey, if BPP parallel NP is equal to sharp P must randomly reduce to NP. If sharp P randomly reduces to NP, then it's in NP/poly intersection co-NP/poly. And if it's in that, then, and it's checkable, which it is because it's sharp P again, then it's in ZPP to the NP. This concludes what I'll be presenting for the proof. The paper is also quite good, I think, recommend reading. There's like several, I think I used Toda's theorem on 3 separate occasions to like hammer this into shape. So it's like a very fun read. Yeah, so then we have this nice result. What can we do with it? Well, the first thing we can do is we can improve the boson sampling result. We can now say the polynomial hierarchy collapses to a level lower than it did. After the Aaronson result came out, there's another bunch of other quantum experiments where people realize the same arguments hold. And so one clean qubit, IQC, they have different assumptions, but if those assumptions hold, then we know that they also cannot be in samp P, can't be sampleable in the classical computer. And that means that if any of those assumptions hold, we get samp BQP is not equal to samp P. And now where else can we apply this? Turns out that also post BQP, i.e. This is now a decision problem, and it's a decision problem where you are doing a quantum computation and post-selecting on a bit. It turns out that if post BPP is equal to post BPP, we get the same collapse. It's the exact same argument, exact same reasoning. And I've put rather cheekily on this slide your future results. It feels like this should extend beyond just the stuff that I had to hand in quantum computing, but I haven't found a place for this yet. So if anyone is doing approximate and exact counting stuff or reading an old paper and they would like to move it down the polynomial hierarchy another level, please think of this result. I love citations. Yeah, so future work. Where else can we apply this counting result? The other assumptions, so the assumptions on the distributions of Gaussians, they might be more hingy. They might be more, they may be more unlikely than this polynomial hierarchy result. Proving those is an ongoing question. One of them gets more attention than the other, but I think if you could erase either of them, that would be very big. If you can erase both of them, then like I become significantly more confident that quantum computing is useful or is not equal to classical computing. And then finally, yeah, this other thing I mentioned, that could we go further down the polynomial hierarchy? It felt like we were at the first level and then we went back up. It might be possible with more care to stay down in MP/poly. Cool. Yeah, and then what I'm working on right now, because I got questions on this, I now work on aligning AGI to human values. If you're interested in doing this and you've always felt like you don't know where to start, come and talk to me. We have like a large amount of money to give away. We have well-defined complexity theory problems to get started on, and we're like super keen for more people to be doing this. So like we have a conference coming up as well, which we're organizing. If you're interested in AGI or alignment work, come and talk to me. I'll be here till coffee tomorrow. Cool, I think that's my last slide.